Thank you so much, Sid. So my name, as Sid said, is Lily Mara. I'm an engineering manager at a software company here in the Bay Area called OneSignal. We're a customer messaging company. We help millions of application developers and marketers connect with billions of users, and we send around 13 billion push notifications, emails, in-app messages, and SMS every single day. A little bit about my history. I started using Rust professionally in 2016, and I started using it as my main daily programming language professionally in 2019 when I started at OneSignal. I'm the author of the book Refactoring to Rust that is available now in early access at manning.com, and hopefully will be going into production relatively soon. So what are we going to be talking about today? We're going to be talking about how we built this scalable, high-throughput timer system at OneSignal. We're going to be talking about the motivation behind building it in the first place, the architecture of the system itself, how the system performed, how we scaled it up, and some future work that we are maybe thinking about doing in the system. So let's jump back in time a little bit. It's 2019. I've just started at OneSignal. I've just moved to sunny California from horrible, not sunny Ohio. And everybody in OneSignal, everybody in the kind of customer messaging sphere is talking about the concept of journey builders. And if you're not a content marketer, you might not know what a journey builder is. So just a quick crash course. This is a no-code system that allows marketers to build out customer messaging flows. So this is a flowchart that's going to be applied at a per-user level. This is very similar to like what a marketer might put together themselves. So over here on the left, we're going to start. Every user is going to start over here, and there's immediately going to be dumped into a decision node. So we allow our customers to store arbitrary key value pairs at the user level. And in this case, a customer might be storing, what's your favorite color as one of those key value pairs. So we'll make a decision based on that. Let's say, for the sake of argument, that this user's favorite color was blue. We're going to send that user a push notification that says, hey, there's a 20% off sale on blue shirts. We know how much you love blue. Aren't you so excited about the blue shirt sale? And then the next thing that's going to happen is we are going to wait 24 hours. We're going to do nothing for a day. This was the missing piece. We kind of thought we understood how to build the event system. We understood how to build the node walking tree, but we didn't have a primitive in place in our network for scheduling, for storing a bunch of timers and expiring them performantly. So this is what we're going to be building today. So after we do that 24-hour wait, we are going to have another decision node. We're going to say, did that particular user click on that particular push notification we sent them? If they did, we will say, mission accomplished, good job, journey, you did the engagement. And if they didn't, we'll send them an SMS that has more or less the same message. And you might want to do this because sending an SMS has a monetary cost associated with it. Carriers will bill you for sending SMS. Twilio will bill you for sending SMS. But push notifications have basically zero marginal cost. So if you want to use SMS, you might want to use it as kind of a second order messaging system to get in contact with your customers. So that's a journey builder. That's what we're going to try to enable the construction of today. So what are the requirements on this timer system that we're going to build? We want to be able to store billions of concurrent timers because we want to be able to support the billions of user records that we already have. We want to be able to expire those timers performantly. We want to minimize data loss because, of course, we don't want to be dropping timers on the floor. We don't want people to get stuck in particular nodes of their journeys. And we want to integrate well with the rest of the data systems that we have at OneSignal. We're a relatively small company. We don't have the resources to have, a team for every particular data system that's out there. We don't want to adopt, 50 completely different, open source data systems. So let's get in the headspace a little bit. We realized very crucially that if we wanted to build a timer, we had to think like a timer. And so we took the project and we set it down for a year and we didn't think about it that hard. And we prioritized other initiatives. Jumping forward once again, we're in the beginning of 2021. And we have the resources to start investigating this project. So we have to make a decision. Are we going to build something completely from scratch ourselves, or are we going to buy a kind of off-the-shelf system? Is there an open source timer and open source scheduling system that we can just use, right? The first place we looked were generic open source queuing systems like Sidekick and RabbitMQ. We already operate Sidekick very heavily. At OneSignal, it's the core of our delivery API and a lot of our kind of lower throughput scheduling jobs. But these general purpose queuing systems, they had a lot of features that we didn't really need. We didn't want to pay to have to operate. And they were lacking in the area that was the most important to us, and that was performance. We didn't think that these systems were going to scale up to the kind of throughput that we were expecting this timer system to have, right? And the published performance numbers for things like RabbitMQ just seemed orders of magnitude off from what we wanted out of this system. We knew from experience what Sidekick was like to scale, and we didn't think that was going to be good enough. And based on the published numbers, we thought that other things weren't going to be good enough. So we opted to build something for ourselves. We're going all the way. Once again, let's look at these requirements, right? We want to be able to store tons of timers, expire them performantly, minimize data loss, and interoperate with the rest of our system. So let's talk about the rest of the systems. What is the prior art for system design at OneSignal? We have a lot of things written in Rust. We actually currently, but not at the time, had a policy around only using Rust for new systems. But at the time, we were also spinning up new services in Go. We use Apache Kafka very heavily for our async messaging applications. And we also use gRPC for all of our internal synchronous RPCs. Also, as a part of the larger Journeys initiative, we were going to be using Scylla, which is a C++ rewrite of Apache Cassandra. So let's talk about the big blocks, how the data are flowing in and out of the system, right? Probably, sensibly, the input to this system is a timer, right? And a timer is an expiry time, a time to end at, and a thing to do once it has ended, an action. So what are the actions? Initially we came up with a pretty short list. That is sending a message, like a notification, email, SMS, in-app message, or it's adding a tag to a particular user. But we realized that we might come up with more actions in the future, so we didn't necessarily want to constrain ourselves to a fixed list. And we also realized that we might come up with actions that had absolutely nothing to do with journeys, absolutely nothing to do with messaging, that this timer system, this scheduler system has a broad range of applicability, and we wanted to leave the door open for us to take advantage of that. So we imposed a new requirement on ourselves. We said we wanted this system to be generic. So given that the system is going to be generic, what is an action? What does it look like? How does it work? In addition to being generic, we wanted it to be simple. So that meant constraining what an action is, even though it's flexible. We didn't want to give people a whole templating engine or scripting library or something like that. We wanted it to be pretty straightforward. You give us these bits and we will ship them off when the time comes. So are we going to let people send HTTP requests with JSON payloads? Well, all of our internal services use gRPC, so probably not that. Maybe there'll be gRPC requests then. But both of these systems suffer from the same in our mind, critical flaw, in that these are both synchronous systems. And we thought it was really important that the outputs of the timer system be themselves asynchronous, right? And why is that? As timers start to expire, if there's multiple systems that are being interfaced with, say notification delivery and adding key value pairs, if one of those systems is down or is timing out requests, we don't want A to have to design our own queuing independence layer in the timer system, or B, have our request queues get filled up with requests for that one failing system, and to the detriment of the other well-behaving systems, right? So we wanted the output of this to be asynchronous. So we opted to use Apache Kafka, which, as I mentioned, is already used very heavily at OneSignal. We already have a lot of in-house knowledge and expertise on how to operate and scale Kafka workloads. It gave us a general purpose queuing system that was high performance. And a really key benefit is it meant that the timer system was isolated from the performance of the end action system, right? Now, what about these inputs? What about the timers themselves? Because all the timers are being written into the same place by us, we can own the latency of those writes. So this can be a synchronous gRPC call. So the interface, broadly speaking, looks like this. External customers make a gRPC request to the timer system. They're going to give us an expiry time, and they're going to give us an action, which is a Kafka topic, Kafka partition, and some bytes to write onto the Kafka stream. And then later on, when that timer expires, we're going to write that Kafka message to the place that the customer has specified. And we'll delve into the magic box of the timer system as we go through this. And hopefully later on, presumably at some point, the team that enqueued the timer will have a Kafka consumer that picks up the message and acts on it. But the really important thing here is the consumer picking up the message and acting on it is totally isolated from the timer system, dequeuing the message and shipping it across the wire. So if a Kafka consumer is down or not performant, that really has nothing to do with the timer system. It's not impacting us at all. So let's delve into the internals of this a little bit. How are we going to store timers after they come across the gRPC interface? How are we going to expire timers to Kafka after they've been stored? What are the key health metrics of the system? Yeah, let's get into it. I'd first like to talk about the timer expiry process. We know we're going to be writing timers to Kafka. We know there's a gRPC service on the other side that has some kind of storage medium attached to it for these timers. And we want to try to build something that's relatively simple, relatively straightforward for pulling these things out of storage and expiring them to Kafka. So how are we going to do this? We came up with this architecture as kind of our first pass. We're still abstracting the storage away. We're going to delve into that in a minute. But we have our gRPC service. We've added a couple new endpoints to it. There's a getTimers endpoint that takes in a timestamp, and it's going to serve us back all the timers that expire before this timestamp. So every minute, this new scheduler box over here, that's a scheduling service written in Rust. It's going to send a gRPC request up to our service, and it's going to say, give me all the timers that expire before 10 minutes into the future. So if it's currently 4:48, we are going to say, give me all the timers that expire before 4:58. It's going to take all those timers, write them into a pending area in memory, have some in-memory timers, and then it's going to expire those out to Apache Kafka as those timers expire. Once they are expired and shift off to Kafka, we are going to send a delete request up to the gRPC service to remove that particular timer from storage so that it's not served back down to the scheduler. So we view this as a relatively simple solution to the problem because we kind of thought that this timer system was going to be pretty tricky to implement in the first place. So we were a bit incredulous when we came up with this kind of solution. We weren't sure how we were going to represent the timers in memory. We weren't sure how we were going to avoid doubling queuing. But once we kind of just coded up a first pass, we realized that it was actually so much simpler and so much more performant than we thought it was going to be. So we basically created an arena for these pending timer IDs in memory. We had an infinite loop with a 1-second period. We pulled all the timers from the gRPC interface, looped over them and checked to see if they were known or not. If they were not known to the instance, we would spawn an asynchronous task using Tokio, use their built-in timer mechanism. When that timer expires, we would produce the Kafka event, delete the timer from the gRPC interface, and then there was a bit of additional synchronization code that was required to communicate this back to the main task so that we could remove that particular timer ID from the hash set. That was kind of the only complicated piece here. But the real service implementation is really not a whole lot more complicated than this. We were pretty impressed that it was quite so simple. But how does this thing actually perform? What do the numbers look like? Using the kind of built-in default Tokio async future spawning and sleep until functions, we tried to spawn 1 million timers and measure both the latency and the memory utilization. We found that it took about 350 milliseconds to spawn 1 million timers, and that ate about 600 megabytes of memory, which is a relatively high amount of memory for 1 million timers. It's about like 96 bytes per timer, which seems a bit heavy, but we decided that this was good enough performance metrics to go out with. So we were not going to invest too heavily at this point in ultra optimizing from here. So what key performance metrics did we identify once we were ready to ship this thing? The first one was the number of pending timers in that hash set, the number of things that we are watching right now. This was really important for us when we started getting out-of-memory kills on this timer instance, because we had not put any back pressure into the system. So, if there were too many timers expiring at, say, 4 o'clock, 4 o'clock rolls around, you try to load those all into the scheduler falls down, scheduler starts back up, it tries to load the timers again, and it keeps falling over. So we use this metric to identify what's falling over at 1 million. Let's tell it to not load any more than 600,000 into memory. And the other one was a little bit less intuitive. It was the timestamp of the last timer that we expired to Kafka. And we use this to measure the drift between the timer system and reality. So if it's currently 4 o'clock and you just expired a timer for 3 o'clock, that means your system is probably operating about an hour behind reality. And you're going to have some customers who are maybe asking questions about why their messages are an hour late. This was kind of the most important performance metric for the system. This is the one that we have alerting around. If things start to fall too far behind reality, we'll page an engineer and have them look into that. Next, I'd like to talk about the storage layer for the system. Thinking about the requirements of this, we wanted to support a high write throughput. The goal that we had in mind was about 10,000 writes per second. And from our experience operating Postgres, we knew that this was definitely possible to do with Postgres, but it was kind of a big pain in the butt if you didn't have a lot of dedicated Postgres staff and a lot of infrastructure dedicated to clustering Postgres. So we didn't really want to use Postgres for this. We wanted something that was going to be simple to scale so that when we needed additional capacity, we could just kind of throw it at the wall and have it stick. We wanted something that would be simple to maintain, so zero downtime upgrades were going to be really important to us. And we knew that we were going to be making relatively simple queries that might serve back a bunch of results. So, what is simple query? What is the kind of queries that we're going to be making? The scheduler, remember, is going to be doing queries that look like, give me all of the timers that are expiring in the next 10 minutes. That is not a very complicated query. It's not, give me all the timers that are expiring in the next 10 minutes for this particular customer that are targeting these 10,000 users in these time zones. Relatively straightforward queries. So we didn't necessarily need all the querying, filtering power of something like Postgres or another relational database. So in the end, we picked Scylla. As I mentioned, this was already something that we were spinning up as a part of the larger Journeys project. So even though we didn't have existing in-house experience operating Scylla, we knew that we were going to be developing it as another business line item. One thing that we had to think about with adopting Scylla was that the data modeling approach for Scylla and Cassandra are very different from something like Postgres. So we need to think pretty hard about how we're going to be writing these data to the tables and how we're going to be querying it afterwards. So when you're doing data modeling in a relational database, it's a lot easier to just think about, what are the data and how do they relate to each other? You can, generally speaking, add any number of joins to a Postgres query and then add any number of indices on the other side to make up for your poor data modeling. You don't really have this luxury with Scylla or Cassandra. They use SS tables. They don't provide the ability to do joins. And there really aren't much in the way of indices other than the tables themselves. So ahead of time, as we were writing the data to the database, we need to be thinking about how we're going to be querying it on the other side. And remember, the query we're going to be doing is fetch all timers about to expire. So what does about to expire mean in this sense, right? If we think about the basic elements that we just said were a part of a timer, It's got an expiry timestamp, it has a binary data blob, and it has a Kafka topic and partition that the message are going to be written to. Quick note here. Most of the architecture work here was done by the Apache Cassandra team, and my exposure to this ecosystem has all been through Scylla, so I'm going to attribute things to Scylla that were certainly done by people on the Apache Cassandra team, and if that was you, I apologize. I'm very sorry. In Scylla, we have data that's distributed amongst a cluster of nodes, and as you query the data in the nodes, generally speaking, each query, we want it to hit a single node. We don't want to be merging data together. We don't want to be searching across all the nodes for particular pieces of data. Generally speaking, we want to know ahead of time where a particular row are going to land in the data structure, in the cluster. So how do we do that? How do we distinguish where a row is going to go? There's a couple different layers of keys that exist on each row in Scylla, and we're going to use those. The primary key has two parts, so just like a relational database, we have a primary key on each row. The first part is the partitioning key. That's going to determine, which node in the cluster a row is going to land on, and where on that node it's going to go. It's going to group the data into partitions that are shipped around as kind of one unit. And this is composed of one or more fields. And there's also a clustering key that determines where in the partition each row is going to go. So that's used for things like sort ordering. And that's optional, but it also can have a variable number of fields in it. Generally speaking, the kinds of queries, the kind of high-performance read queries that we want to be doing, you need to include the partition key, an exact partition key, in each read query that you're doing. So you're not having like a range of partition keys. You're not saying, give me everything. You need to provide, give me this partition key. And remember, again, query we're performing is get all the timers about to expire. So what does about to expire mean? It means we need to pre-bucket the data. We need to group our timers into buckets of timers that expire around the same time so that we can query all those timers together. We're going to be bucketing on 5-minute intervals. So for example, a timer expiring at 4:48 p.m. and 30 seconds, we're going to bucket that down to 4:45. And everything between 4:45 and 4:50, those are going to land in the same bucket. We are still going to store the expiry time, but we're also going to have this bucket that's specifically going to be used for storage locality. But we can't have the bucket alone be the primary key because, just like every other database that's out there, primary keys need to be unique in tables. So if the 5-minute bucket was the sole primary key, you can only have one timer that existed per 5-minute bucket, and that's not a very good data system. So we're going to introduce a ID field, a UUID field that's going to be on each row, and that's going to take the place of the clustering key. So that's going to determine, again, where in the partition each row is going to land. So our final table design looked like this. We had those same 4 fields that we talked about initially, but we also introduced 2 new fields, this row UUID field and the bucket field, which is, again, the expiry timestamp rounded down to the nearest 5 minutes. And you can see that on the primary key line down there, we have first the bucket field, that's the partitioning key, and second, we have the clustering key field, which is the UUID field. So what do the queries look like that we're going to be doing on this table? We're going to be getting all the fields off of each timer row inside of each bucket, inside of this 5-minute bucket that's starts at 4:45. But the eagle-eyed among you might already be noticing a problem with this. If it's currently 4:48 and we get the timers that are in the bucket starting at 4:45, how are we gonna do this 10-minute look-ahead interval thing? How are we gonna fetch the timers that start at 4:50 and 4:55? Because a 10-minute interval isn't necessarily gonna span more than one 5-minute data bucket. And further complicating things, this system is not necessarily always real time, right? it might be the case that this system is so far behind reality, which, in some cases that might only be a couple seconds, but it might be the case that there are still some existing timers that are falling into buckets that already, ended, right? If it's 4:45 and 10 seconds, and you still have an existing timer that was supposed to expire at 4:44 and 59 seconds, you still have to be able to fetch that out of Scylla, because maybe the scheduler is going to restart and it's not going to be able to use the one that's floating around in memory. So how are we going to pull all the buckets and get the data? We can't just query the currently active bucket. We need to find out what buckets exist, which buckets that exist fall within our look-ahead window, and we need to query all of those for their timers. So we introduced another table, a metadata table, that was just going to hold every single bucket that we knew about. So this is going to be partitioned just by its single field, the bucket timestamp. And this was just going to give us access to query what buckets currently exist. So every time we insert data into our tables, we are going to do two different writes. We're going to store the timer itself, and we're also going to do an insertion on this bucket table. Every insert in Scylla is actually an upsert, so no matter how many millions of times we run this exact same query, it's just going to have one entry for each particular bucket, because they all have the same primary key. So what do our queries look like? We're first going to have to query every single bucket that exists in the database, literally every single one. And that's going to come back into the memory of our gRPC service. And we're going to say, of those buckets that exist, which ones fall into our look-ahead window. That's going to be the 4 buckets from 440 to 445. And we're going to query all the timers off of those, and we're going to merge them in the memory of the gRPC service and then ship them down to the scheduler. So if we put this all together into one kind of cohesive system view, on the external team side, we have a thing that creates timers. That's going to send a gRPC request across the wire to our service. That's going to store a timer in our Scylla database alongside a corresponding bucket. Then every minute, our scheduler is going to call the getTimers gRPC method with a look-ahead window. It's going to add the timers that fall into that window to its pending area in memory. And when those in-memory timers expire, it's going to write them out to an Apache Kafka topic. And eventually, maybe, there will be a Kafka consumer that picks that message up. So this system, as I've described it, existed for about a year, maybe a year and a half, without any major issues, modulus that out-of-memory problem. And we didn't have to do any major scaling operations. It didn't have any really big problems. We mostly just didn't think about it after it was out there and running. We're pretty happy with it. But eventually, we started to think about adding more users to our Journeys product. We started to think about using this timer system to support more use cases than just Journeys. And we realized that we would have to do some scaling work in this, because what I've described has some kind of poor scaling tendencies. So to describe that work, I'd like to invite Hunter up to the stage to finish that out.
Great. Thank you, Lily. All right, hi, my name is Hunter Laine. I've been an engineer on Lily's team at OneSignal for about 2.5 years. And in a past life, I was a marketing operations manager in Prague. So we're going to take another leap forward in time to Q1 of this year. We have this effective timer service up and running pretty smoothly. It's capable of storing billions of concurrent timers and expiring them in a performant manner, while minimizing data loss and easily integrating with the rest of our systems. It's essentially a set timeout function that's available across our entire infrastructure without any use case specific limitations. Sounds pretty good, right? We thought so too. So we decided it was time to actually start doing that integrating with the rest of our systems. As Lily mentioned, we send about 13 billion notifications a day. So we wanted to use the timer service to ease a significant amount of load on our task queues. This could be useful for a myriad of things, from retrying requests on failures across multiple services, to scheduling future notifications, and many other areas we were already excited about. But if we were going to use the timer service in these many critically important areas, we needed to ensure that it could handle a lot more timers reliably than it currently could. We needed to scale up. So, as we mentioned before, the original motivation for and use of the timer service was to enable these journey builders, no-code systems generally used as a marketing tool. Now, these systems constituted a significant number of timers that we were storing and retrieving. However, when compared to the task of integrating with our delivery systems, it represented a relatively small scale of use. And at this scale of use, we had opted for this. Slightly more simplified architecture to avoid dealing with the more complex coordination required to make the timer service fully scalable. And specifically when we talk about scaling issues, we will be focusing more on the scheduler portion. Now, scaling the timer service vertically was no problem at all. We could and did add resources to both the gRPC service portion and the scheduler as needed. Now, scaling the gRPC service portion horizontally was also no trouble. We could easily add a pod or 4 to handle an increase in create, get, and delete requests for multiple clients. The slight hitch that we were now facing was that the scheduler was not quite so simple to scale horizontally. We'd not yet done the work to allow for multiple schedulers to run at the same time. See, each scheduler needs to ask the gRPC service for timers at some set interval. But it does no one any good if each individual scheduler is asking for timers and getting all the same ones back. Then we're just duplicating all the work, and each one is, instead of sharing the load. Plus, it certainly doesn't seem like a desirable feature to enqueue each message to Kafka multiple times, as we see here. We needed to do a bit of a redesign to allow for multiple schedulers to share the task of scheduling and firing timers, with each in charge of only a particular subset of the overall timers. So how do we do that? If we wanted multiple schedulers to run in conjunction, we needed to find a way to group timers by more than just time, so that those schedulers could be responsible, each one, for requesting and retrieving only a particular group of timers. So first, we needed to make some adjustments to how our data was stored, so that timers weren't stored just by the time that they were to be sent out, those 5-minute bucket intervals, but by some other grouping that different schedulers could retrieve from. So we made some adjustments to our Scylla table schemas so that when a new timer is created, it is inserted into a bucket by both that time interval and now a shard. While we were adjusting these schemas, we also actually decided to shrink that bucket interval from the 5 minutes we'd been using to 1-minute bucket intervals. And this was because we were already noticing that our Scylla partitions were getting larger than we would like. We would like to keep our Scylla partitions in general relatively small, as this leads to more efficient and less resource-intensive compaction. We determined which shard a timer belonged to by encoding its unique UUID to an integer within the range of the number of shards we have. We actually have our shards set to 1,024, with timers pretty evenly distributed among them. Each scheduler instance is then responsible for an evenly distributed portion of those shards. Now, we went to this sort of granularity in this many shards, also in an effort to keep those Scylla partitions relatively small. Now, this means we have a more efficient way to parse a far greater number of timers. This update also makes the bookkeeping of the buckets table much more efficient and means that when querying for timers, we look much more particularly at a particular shard and time to retrieve from. We then just needed to adjust our get timers request so that when we do request those timers, we do it not just by time as we were before, but in addition by that shard so that we can get a particular subset of the overall timers. Great. So we now have a system whereby timers are stored by both time and shard, and a way by which to retrieve those timers by both time and shard. We're there, right? Just one big problem. Each scheduler instance needs to have state so that it can reliably ask for the same subset of timers every time it asks. But how does each scheduler know who it is? This was important because if a scheduler instance were to restart for any reason, it needed to start back up as the same scheduler so it could pull the same timers. If we have multiple instances pulling the same subset of timers, we're kind of back at square one. if scheduler 2 were to restart for any reason, now thinking that it's scheduler 1, when we already have a scheduler 1 up and running and pulling timers for scheduler 1, we're again duplicating work and erroneously firing timers multiple times. Plus, even worse here, no one is looking after the shards assigned to scheduler 2. So in order to solve this, we deployed a new version of the scheduler as a stateful set in Kubernetes, which, among other things, gave us a stable, unique name for each instance of the scheduler every time it started up, with each name ending in a 0-indexed value up to the number of replicas. Each scheduler could then take that value and calculate a range of shards that it's responsible for retrieving timers from. Importantly, this means that each shard of timers, and therefore each individual timer, will only ever be retrieved by one scheduler instance. So we now have this system where we store timers by both time and shard, where we have retrieval requests that can get a subset of timers by both time and shard, and now schedulers that have state and can therefore reliably request the same subset of timers every time they ask. We have achieved full scalability. So with these changes made to the architecture of the timer service, adding new nodes to the scheduler is as simple as increasing the replica count in the config file, which makes scaling the timer service both vertically and horizontally possible and simple to do as we continue to use it in more and more parts of our system. Because we now have multiple instances of both the gRPC service portion and the scheduler, we've made the timer service much less susceptible to serious outage if a node were to go down. Previously, we only had one scheduler, so if it went down, that was kind of it. There were no timers being retrieved or processed or fired, and no messages being enqueued to Kafka by the timer service until that node were to restart. Now, because we have multiple instances, each in charge of only a particular subset of the overall timers, if a node goes down, it has much less impact on the overall functioning of the system. On single port performance, each scheduler node is capable of handling about 10,000 timers per second, and frankly, that's without even pushing it, which makes horizontally scaling incredibly powerful. Each gRPC instance handles about 17,000 requests per second, really without trouble. There are a few things to note about our timer service as it exists today. First, the timer service has an at least once guarantee. And this is because there's a space between the scheduler in queuing its message to Kafka, and it then turning around and requesting that that timer be deleted, if the scheduler were to restart for any reason between those two actions, or if the gRPC service has some sort of communication error between the scheduler or between Scylla when processing that delete, the timer will fail to be deleted and will again be retrieved and fired. Because of this, the timer service does expect that all downstream consumers manage their own item potency guarantees. Another call out about the timer service is that timers will fire close to, but not exactly at the time they're scheduled. And this is because schedulers still need to pull in timers at that periodic interval via that get timers request. I think as Lily mentioned, we currently have each scheduler set to pull in the next 10 minutes of timers every 1 minute. Possibly the biggest call out about the timer service as it exists today is that once a timer has been retrieved by the scheduler, there's no method by which to cancel it. This is because the only way to delete or cancel a timer in this system, the way we have it currently, is via that delete timer request on the gRPC service, which deletes from the database. Therein, if the timer's already been retrieved from the database and is now in the scheduler, there's no way to currently stop it from firing. The timer service has proven to be incredibly powerful within our own internal systems, and as such, we really believe it could be useful to other organizations and individuals, so there's definite potential that we will move to open source it in the near future. As we continue to grow as an organization, we intend to use the timer service as we create new services, but want to dedicate resources to integrating it more broadly across our existing infrastructure in order to streamline. We also would like to add and fine-tune features such as perhaps the ability to cancel a timer at any point in the lifecycle. We're about 4 years on now from that original conception of a timer service to enable those journey builders. We now have an incredibly robust system that's capable of storing billions of concurrent timers and expiring them in a performant manner, while minimizing data loss, easily integrating with the rest of our systems, and, importantly, scaling simply both vertically and horizontally to accommodate our future use. Thank you so much for joining us today. If you'd like to get in touch with me, my LinkedIn is here. If you'd like to get in touch with Lily on any of her socials or buy her book, her information's here. And we would love any feedback on the app. So I think we have a few minutes for questions.
Yeah, I think we ended perfectly on time.
Great.
How did you handle when you added the new nodes to the scheduler? So if you have 4 running, you each get 250 shards, right? You add a 5th one, now they only get 200. How did you keep them from stepping on each other's toes and increase that number?
Yeah, so we would take all of the nodes down at the time that a restart occurred and start them back up. So there would maybe be 30 seconds of potential timer latency. We weren't super concerned about millisecond accuracy of the schedulers in this case.
Good question.
One of the interesting places for scheduling interesting is operating systems, and there's an interesting data structure in there. It's referred to as a delta queue, where instead of actually storing buckets of timers, you actually store the offset. So every time you have a clock tick, you just have to pop off the first n number of timers to handle it. Did you explore that idea when you were evaluating different solutions, or? And how did you decide to come up with, figure out your implemented solution?
Yeah, so I was the manager on the team that at the time we were initially building out this project. And the engineer that was in charge of the implementation, he was running all these complicated data structures past me. And I suggested, did you try the most naive possible approach? Did you try, spawn a future and, wait on a task? And he was like, well, that can't possibly perform well enough, for our needs. And I said, well, why don't you try it and we'll see if it performs well enough. And it did. So we actually, didn't really continue to evaluate more complicated data structures because the easiest one worked for us.
Okay.
Lily, I think that one of the most annoying things to work with time zones, with anything related here. Did you sidestep or how did you handle it?
Yeah, so that was totally sidestepped. These timers were all in UTC. These were all server-side events. Everything that is happening here is something, like every timer that's in this system is a timer that was scheduled, by another team at OneSignal. So if somebody cared about something being, time zone sensitive, they cared about, you send a notification at 8 a.m. in the user's time zone, they would have to figure out when 8 a.m. in the user's time zone was on a UTC clock. Good question.
Hey, you mentioned that you have a secondary table where you store all the buckets, and you fetch all the buckets in the system.
Yes.
Which you call for the next interval you want to fetch. So that's essentially like a full table scan.
Yes, that is basically a full table scan. The thing that's kind of saving us from, really having a bad time on that is the fact that the number of entries on that table is, much more constrained than, say, the number of entries on the timers table, right? There's going to be a maximum of 1 entry on that table for every 5-minute interval. And I don't think the timer system actually has a limit on how far out you can schedule timers, but I believe the systems that enqueue timers currently, and maybe we should revisit this, but the systems that currently enqueue timers, I believe do have limits on how long they will allow you to schedule out a timer. So like Journeys will not allow you to say, send a notification and then wait for 30 days. So that just puts a constraint on the number of things that are allowed to live in the data set. But yes, it's potentially very expensive.
Thank you, very nice talk, by the way. So I have a quick question regarding your database structure itself. So it's on Scylla, which is the remake of Cassandra,
Yes.
right? So it must be more performant than Cassandra because it's Java-based inherently. So at the back end, how many nodes do you have and what the replication factor is? And do you have multiple data centers with the same image of nodes that do the real-time replication?
Yeah, so we have just a single data center. I believe for timers we have,
I think it's 6.
I think 6 nodes, yeah, with,
For Scylla, yeah.
do you know what the replication factor is?
I don't off the top of my
Gosh,
head.
I don't know what it is off the top of my head either. I'm not sure if we did any of our own benchmarking of Scylla versus Cassandra. I think at the time our CTO had quite a strong aversion to Java. So I believe we actually run 0 Java code in production, and adopting Scylla versus Cassandra was partially motivated by that desire. We have been quite happy with Scylla since we've adopted it.
Yeah, two of you on opposite ends of the question.
So many questions. Lots of good questions.
You mentioned you had a 5-minute bucket, and then the scheduler was putting ahead for the next 5 minutes.
Yes.
The processing it, right? So was it like recurrently putting again after it has processed once until the bucket is empty? Because even the timer should be registered in the interval while it was processing it.
Yes, so that's a good question. So a timer would be returned by the gRPC service multiple times until it was expired, until that delete timer method was called for that particular timer. So that, I suppose, is another inefficiency of the system, right? There's a bunch of data retransmission. And again, this was done in the name of kind of the simplicity of the system, and that is something that probably could be removed in the future if we wanted to optimize that a bit more.
Okay, this will be our last question, and then I assume there's happy hours.
Really appreciate the talk. It strikes me that there is a possibility here where there's some crashing bug in a particular timer. One of your scheduler nodes can get stuck just in a crash loop. Do you have a mechanism for recovery from that? Or is that just not been a problem?
That hasn't been a problem for us. I think because the API of a timer is so small, the things you are allowed to have are, the variance in each timer is, time and data and Kafka settings, basically. And we don't give you more Kafka settings than topic and partition. So the attack surface is really small. We haven't had any instances of a malformed timer that was causing issues for the service. But yes, if a particular node of the timer system was just crash looping, we would, basically just have to page an engineer and have them look into it. There's not kind of auto healing built into it.
Thank you everyone for the great questions, and thank you to the manager for the talk.
Thanks for coming, everyone. Good job.
You too.